Welcome back, everyone, to another deep dive. Today, we are going to zero in on something that's absolutely crucial, absolutely fundamental when it comes to helicopter flight, safety, and performance.
Yeah.
We're talking about weight and balance.
Yeah, weight and balance.
Now, we've got some really fascinating material here that we've pulled from a weight and balance handbook, specifically for helicopters.
Good stuff.
And what's so interesting about it is just how much more critical this whole issue of weight and balance is
Right.
for rotorcraft compared to your everyday airplane.
Absolutely. Both aircraft need careful loading, no question.
Yeah,
But in a helicopter, the consequences of being outside those limits can be much faster acting and more pronounced just due to the way it generates lift and stays controlled. It's a whole different ballgame.
exactly. So, today, our mission, if you will, is to really get under the skin of why proper loading in a helicopter isn't just, a good idea.
Right.
It's absolutely vital.
Oh, it's essential.
And we want you to see, as a listener, how even what might seem like minor shifts in weight distribution can have really serious ripple effects,
Huge.
throughout the aircraft.
Yeah.
And ultimately, that's going to give you a much deeper appreciation
Yeah.
for the incredible precision
Yeah.
that goes into every helicopter operation.
Yeah.
So, we're going to be looking at the nuts and bolts here, things like basic empty weight, the center of gravity CG, both fore and aft and side to side,
Yep. Yep.
those crucial CG range limits, the maximum allowed weight,
Right.
where everybody sits in the helicopter, how much baggage you can carry and where it goes, and
Yeah.
even, fuel and oil capacities. Now, it might sound like a lot of numbers,
Sure.
but trust me, they tell a really gripping story
Oh, yeah. Absolutely.
about how these incredible machines actually take to the air and
Yeah.
stay controllable.
Mm.
So let's just unpack this right away, okay?
Okay.
What is it about helicopters that makes weight and balance so much more critical
Right.
than for airplanes?
Well, the handbook gets straight to the heart of it by emphasizing that it's far more critical and that helicopters have a much more limited CG range.
Uh-huh.
Airplane designs tend to be more forgiving when it comes to how weight is distributed within the fuselage.
Yeah.
Helicopters, however, are all about the pilot's ability to precisely manage that rotor disc using the cyclic stick. So the engineers who design these aircraft meticulously calculate exactly how much cyclic control authority
Right.
the pilot will have. And based on that, they establish very tight longitudinal that's along the length of the helicopter
Okay.
and lateral that's side-to-side CG envelopes.
Got it.
Think of these envelopes as like very specific zones.
Oh, really?
The center of gravity has to stay within these zones to guarantee the pilot's got enough control for all parts of the flight.
And it's really interesting. They highlight both longitudinal and lateral CG as being so crucial.
Yeah.
With most airplanes, the focus seems to be primarily on just the fore and aft balance.
Right, right.
Why is that side-to-side aspect so much more important for helicopters?
That's a fundamental difference. While a lateral imbalance in an airplane might affect, the trim or how much you need to adjust the controls to fly straight in a helicopter, it can have a much more direct and immediate impact on control and stability.
Got it.
The handbook specifically points out certain helicopters, particularly those involved in hoist operations where they're lifting external loads,
Oh, interesting.
are especially sensitive to lateral CG.
Okay.
So picture this. If you're hoisting a heavy object off to one side,
Yeah.
that's going to create a significant sideways pull, a lateral imbalance
Right.
that the pilot has to actively counteract using the cyclic.
Okay.
If the CG is already too far to one side, the pilot could simply run out of control authority to maintain a level attitude, or critically to prevent a very dangerous situation called dynamic rollover.
Dynamic rollover. That doesn't sound good at all.
It's not a good thing.
So just to keep our bearings here, talking about the center of gravity and to measure that accurately, we need a consistent reference point.
Absolutely. A fixed reference.
The handbook mentions this thing called the datum.
Right.
What exactly is the datum?
Precisely. Just like with airplanes, helicopters use a datum as a fixed reference point to measure the location of all the different components and ultimately the aircraft's overall center of gravity.
Okay.
The handbook points out that for most modern helicopters, this datum, often designated as FS 0.0, which stands for Flight Station 0,
Okay.
is located ahead of the physical aircraft itself usually at or near the nose.
Uh-huh.
This is a bit of a change from some older helicopter designs where the datum might have been situated at the rotor mast.
Oh, interesting. Okay.
Having the datum forward is interesting because it means that most of the distances, or what we call arms in weight and balance calculations,
Okay.
will be positive values,
Yeah.
which simplifies the math a little.
Okay, so the datum is our 0-inch mark
Yes.
for measuring everything fore and aft.
Exactly.
What about side to side?
Right.
The handbook mentions butt line 0.
Right. For those lateral side-to-side measurements, they use butt line 0, or BL0.
Yeah.
Imagine an invisible vertical plane slicing right through the exact center of the helicopter from the very front to the very back.
Okay, got it.
Distances measured to the right of the center line are considered positive,
Uh-huh.
and distances to the left are negative.
Okay.
Just like with the longitudinal measurements, these lateral arms are then used in calculations to determine the lateral center of gravity.
Got it.
The resulting lateral moments tell us about the helicopter's tendency to want to tilt or roll to one side or the other.
Oh, okay, interesting. So it's a similar principle to
Yeah.
how we figure out the empty weight and empty weight CG for an airplane using scales and calculating moments,
That's right.
but with that crucial added dimension of lateral balance
Absolutely.
for the helicopter.
Exactly. The process involves weighing the helicopter at several specific points. Then they use the precise distances from both the longitudinal datum
Yeah.
and the lateral butt line 0 to calculate what are called moments. Think of a moment as the twisting force created by a weight
Right.
acting at a distance. A heavier weight further away creates a larger moment, which is why location is just as important as the weight itself.
Interesting.
Once they have all the individual moments, they add them up to get the total moment
Okay.
in both the longitudinal and lateral directions. Finally, they divide the total moment in each direction by the total empty weight of the helicopter to find the exact location of the empty weight center of gravity,
Yeah.
both how far forward or aft it is and how far to the left or right it is.
Got it.
This empty weight and empty weight CG then become the crucial starting points for every subsequent weight and balance calculation you'll do for a specific flight.
So we've got the baseline established with the empty weight and CG.
Yes.
Now, what actually happens if the weight isn't distributed correctly along that longitudinal axis?
Right.
If the CG ends up being too far forward or
Yeah.
too far aft?
Well, the handbook provides some very clear illustrations of the potential consequences. If the CG is too far forward, the helicopter will naturally want to tilt nose down.
Okay.
The pilot will have to actively use rearward pressure on the cyclic control just to maintain a level hover.
Yeah.
But here's where it can get really tricky.
Okay.
If the CG is too far forward,
Yeah.
the pilot might simply run out of rearward cyclic authority during landing to properly execute the flare that's the critical maneuver where you raise the nose just before touchdown to slow your rate of descent.
Right.
If you don't have enough rearward cyclic, you could end up with a higher landing speed,
Yeah.
potentially leading to a hard landing and even aircraft damage.
Wow.
You've lost that critical margin of control when you need it most.
So you're using up all your available control
Exactly.
just to maintain level flight,
Yep.
leaving nothing in reserve for maneuvering.
Yep.
What about the opposite scenario if the CG ends up being too far aft?
Well, an aft CG can be just as dangerous, if not more so. The handbook mentions that the helicopter will tend to fly with an excessive tail-low attitude.
Okay.
In a hover, the pilot might need to apply more forward pressure on the cyclic than is actually available, especially if there's no wind to help stabilize things.
Right.
There's also a significant risk of the tail boom striking the ground, particularly during certain maneuvers or on uneven terrain.
Ooh, yeah, I can imagine.
And critically, in high-speed forward flight, if a sudden gust of wind causes the nose to pitch up unexpectedly,
Yeah.
there might not be enough forward cyclic control left to safely lower the nose back down.
Yeah, you're basically, that's a situation you absolutely want to avoid losing control at high speed due to an imbalance.
Totally. Yeah, imagine scraping the tail boom on landing.
Yeah.
A direct result of poor weight distribution.
So both extremes of longitudinal CG have some pretty serious and direct safety implications.
Very serious.
And we touched on lateral CG earlier,
Yeah.
the increased risk of dynamic rollover.
Right.
Can you maybe paint a clearer picture of why an improper lateral CG makes that more likely?
While the handbook doesn't delve into the intricate mechanics of dynamic rollover, it correctly highlights the increased hazard when the lateral CG is outside the approved limits.
Yeah.
Essentially, dynamic rollover is a unique phenomenon in helicopters that can occur while on the ground or during very low speed maneuvers when one of the landing gear, skids or wheels, becomes a pivot point.
Okay.
If there's a significant lateral imbalance, meaning the weight is heavily skewed to one side,
Yeah.
it requires much less external force or pilot input to cause the helicopter to roll over onto its side.
Like,
The pilot might simply not have enough lateral cyclic authority
yeah.
to counteract that tipping force, especially if the CG is already biased in that direction.
Yeah.
It's a rapid and often unrecoverable event.
Incredibly precarious.
Very much so.
Now, the handbook also makes this important point that simply staying below the maximum certified gross weight
Right.
isn't the only piece of the puzzle.
No.
Factors like density altitude
Yeah.
can also have a significant impact.
Huge impact.
How does that come into play with weight and balance?
Well, that's a crucial consideration. The approved maximum gross weight for a helicopter is determined under what are considered standard atmospheric conditions,
Yeah.
a specific temperature and air pressure.
Okay.
However, on hot days or at high altitudes, the air becomes less dense.
Right.
That's what we refer to as high density altitude.
Got it.
This thinner air has a direct negative impact on the helicopter's performance capabilities.
Uh-huh.
Most notably, the amount of power the engine can produce and the efficiency of the rotor blades in generating lift.
Makes sense.
As a result, the actual safe maximum weight that the helicopter can lift and operate within safely is reduced under these conditions. This affects virtually every phase of flight. Getting off the ground in a hover, takeoff, climbing, performing an auto-rotation in case of engine failure, and landing safely.
Right.
A helicopter that might be perfectly within its maximum gross weight limits on a
Yeah.
cool day at sea level
Yeah.
could be dangerously overloaded and unable to perform safely under conditions of high density altitude.
Got it.
So pilots absolutely must factor in these environmental conditions when calculating their maximum allowable takeoff weight.
So it's not just about the weight of the passengers and cargo.
No,
The environment itself plays a critical role in determining what's safe.
absolutely. Environment plays a huge role.
Now, let's talk about something that changes during flight fuel.
Right.
It seems like something as seemingly straightforward as burning off fuel
Yeah,
can also have an effect on the CG, right?
absolutely. The location of the fuel tanks relative to the helicopter center of gravity is a key design consideration. The handbook points out that in some helicopter designs, the fuel tanks are positioned behind the CG.
Yeah.
What this means is that as fuel is consumed during flight, the weight at the rear of the helicopter decreases,
Right.
and consequently, the overall center of gravity will shift forward.
Got it.
In certain cases, this forward shift in the CG as fuel is burned can become significant enough that by the time the helicopter is approaching its landing with a reduced fuel load,
Yeah.
the pilot might not have sufficient rearward cyclic authority remaining to execute a proper flare and ensure a smooth, controlled landing.
Okay.
That's why for these types of helicopters with fuel tanks located aft of the CG, pilots need to perform weight and balance calculations, not just for the takeoff weight with full fuel,
Yeah.
but also for the anticipated landing weight with the expected remaining fuel.
Interesting. Okay.
They need to ensure that the CG remains within the approved limits throughout the entire flight envelope.
That's a really important nuance,
Very important.
Thinking ahead to how the weight distribution will change
Right.
as the flight progresses.
Absolutely.
Now, the handbook provides some really helpful illustrative examples with figures.
Yeah.
So let's start by walking through that initial loading scenario presented in figure 8-4.
Okay.
What are the starting conditions in that example?
Okay. So in this particular example, we begin with a helicopter that has a basic empty weight of 1,545 pounds. Its empty weight longitudinal CG is located 101.4 inches aft of the datum,
Okay.
and there's also a slight lateral offset in its empty weight CG.
Okay.
Then the scenario involves adding a 200-pound pilot at a specific seat location, a 170-pound passenger in another seat, and a full load of fuel 48 gallons, which weighs 288 pounds in the fuel tanks. Critically, the handbook provides not just the weight of each of these items, but also its longitudinal arm, the distance forward or aft from the datum, and its lateral arm, the distance to the left or right of the butt line 0.
Okay.
So you got all the pieces there.
And then the next step is to do the math to calculate the total weight of the helicopter with this load and the location of the overall center of gravity. Right?
Exactly. For each item, the pilot, passenger, and the fuel, You multiply its weight by its longitudinal arm to determine its individual longitudinal moment.
Okay.
You do the same for the lateral weight and arm to get the lateral moment. Then you sum up all the individual weights to arrive at the total gross weight of the helicopter for this loading, which in this example comes out to 2,203 pounds.
Okay.
You also sum up all the individual longitudinal moments. To find the loaded longitudinal CG, you then divide this total longitudinal moment by the total gross weight.
Yeah.
In this initial scenario, the loaded longitudinal CG calculates to be 94.4 inches after the datum.
Got it.
They perform a similar calculation using the lateral arms and weights to find the total lateral offset moment, which in this case is negative 1,705 pound-inches.
Okay.
The negative sign indicates a slight weight imbalance to the left of the butt line 0.
So the crucial step after all that calculation is to take these resulting CG values,
Right.
the longitudinal CG of 94.4 inches after the datum,
Yeah.
and the lateral offset moment of 91,705 pound-inches.
Yep.
And compare them to the approved CG envelopes
Exactly.
that are graphically depicted in Figure 8-3.
Right.
What does that comparison reveal?
So the analysis shows that when you plot the total weight of 2,203 pounds against the calculated longitudinal CG of 94.4 inches, that specific point falls within the designated approved area of the longitudinal CG envelope shown in Figure 8.3.
Okay.
Similarly, when you plot the same total weight against the calculated lateral offset moment of negative 1,705 pound-inches, that point also resides within the approved lateral offset moment envelope in the same figure.
Okay.
Therefore, this initial loading configuration is confirmed to be within the safe operating limits for both longitudinal and lateral balance.
Okay. So for this initial setup, everything is within the approved limits.
It is.
For takeoff. But then, in Figure 8-5, the handbook looks at what happens during the flight after a certain amount of fuel has been consumed
Right.
and the passenger has gotten out of the helicopter.
Right.
What are the new conditions they are examining?
Right. For this second scenario, they consider that 26 gallons of fuel have been used, which reduces the remaining fuel weight to 132 pounds, representing 22 gallons left in the tanks.
Okay.
Additionally, the 170-pound passenger has deplaned. The pilot, however, remains in the helicopter. This change in weight and distribution brings the new total gross weight of the helicopter down to 1,877 pounds.
Okay.
The next step is to recalculate the longitudinal CG and the lateral offset moment
Right.
based on these new weights and the respective locations.
And what are the results of those recalculations under these new conditions?
This is where the example highlights the sensitivity of helicopter weight and balance. The newly calculated longitudinal CG is 98.2 inches aft of the datum.
Okay.
And the new lateral offset moment is plus 1,699 pound-inches. Notice that the lateral offset has not only changed in magnitude, but also in direction. It's now a positive value, indicating an imbalance to the right of the butt line 0.
Got it. So, and when these new calculated values are compared against those crucial approved operating envelopes in Figure 8-3, what does the handbook show?
Unfortunately, the comparison reveals that both the longitudinal CG and the lateral offset moment now fall outside of the approved operating areas.
Oh, wow.
The longitudinal CG of 98.2 inches after the datum is now too far aft.
Right.
Which, as we discussed earlier, increases the potential for those excessive tail-low attitudes in flight and raises the risk of the pilot not having enough forward cyclic authority for proper control, especially in certain flight regimes. Furthermore, the lateral offset moment being too far to the right indicates a potentially dangerous lateral imbalance, which could lead to lateral control issues and a significantly increased risk of dynamic rollover, particularly during low-speed maneuvers or on the ground.
So even though the helicopter is now lighter overall, the shift in where that weight is concentrated has pushed it into a potentially unsafe operating condition.
Wow, that really drives home just how incredibly sensitive helicopters are to even seemingly minor changes in how the weight is distributed.
It really does.
Just one passenger getting out and some fuel being burned was enough to push the aircraft outside of its safe operating envelope.
Exactly.
So what's the solution in a situation like that? Figure 8-6 in the handbook illustrates a possible corrective action, doesn't it?
Yes, exactly. To bring the helicopter back within the acceptable operating limits, the example considers the option of adding ballast weight or having a different passenger board the aircraft.
Okay.
In Figure 8-6, They show the calculations based on adding either ballast or a passenger weighing 150 pounds.
Okay.
With this added weight, along with the pilot and the remaining 22 gallons of fuel, the new total gross weight of the helicopter becomes 2,027 pounds.
With this revised loading, the recalculated longitudinal CG is 95.0 inches aft of the datum,
Yeah.
and the lateral offset moment is now negative 731 pound-inches, which is a much smaller imbalance, and back to the left side.
So, and does this new configuration with the addition of ballast or another passenger
Right.
bring everything back into the safe operating zone according to Figure 8.3?
It does indeed. When these newly calculated values,
Yeah.
the longitudinal CG of 95.0 inches and the lateral offset moment of negative 731 pound-inches at a weight of 2,027 pounds are plotted on the CG envelopes in Figure 8.3,
Uh-huh.
both the longitudinal CG and the lateral offset moment now fall within the approved area.
Okay.
This clearly demonstrates how carefully even seemingly routine changes in loading need to be considered,
Yeah.
and how the strategic placement of ballast weight, passengers, or cargo can be absolutely necessary to maintain the helicopter within its safe operating limits for
Yeah.
weight and balance.
So, the really crucial takeaway for anyone listening is that weight and balance in helicopters is far more than just making sure you're under the maximum allowed weight.
Absolutely.
It's this incredibly precise balancing act.
It is.
And even what might seem like small adjustments, like someone getting out of the aircraft
Right.
or the normal process of fuel consumption,
Yeah.
can have really direct and significant consequences for the helicopter's overall safety and how controllable it remains.
It is the core message, really. It's a constant and critical consideration for pilots and the engineers who design and maintain these aircraft, both before the helicopter ever leaves the ground and often during the flight itself.
Yeah.
They aren't just checking the total weight on a scale. They are meticulously calculating exactly where that weight is distributed throughout the aircraft
Right.
to ensure that the center of gravity remains within those very tightly defined
Yeah.
and approved limit.
This deep dive
Yeah.
really provides, I think, a much greater appreciation for all the intricate details
It does.
and calculations that pilots and engineers have to take into account
Yeah.
every single time a helicopter prepares to take to the skies.
Absolutely.
It's clearly a far more involved process
Yeah,
than simply stepping into the cabin and taking off.
absolutely. It's a testament to the engineering and operational discipline involved in helicopter aviation.
So considering just how incredibly sensitive helicopters are
Mm-hmm.
to even seemingly minor shifts in weight and balance,
Right.
it really makes you wonder what other factors that might appear to be relatively small or insignificant
Yeah.
could actually have outsized impacts
Yeah.
on their overall operation and safety.
Mm-hmm.
Perhaps, subtle changes in aerodynamic conditions,
Right.
or maybe even, the seemingly minor effects
Yeah.
of day-to-day weather patterns,
Mm-hmm.
or even the critical precision
Right.
required in their maintenance procedures.
It's amazing how much goes into it.
It's definitely some fascinating food for thought. Thanks for joining me for this deep dive.
Absolutely. It's been a pleasure.
We'll see you on the next one.
Looking forward to it.